Okay, now that we have reviewed both some properties of rational numbers and rational expressions in terms of taking fractions of integers or fractions of polynomials and doing things like reducing fractions, add, subtract, multiply, and divide fractions, and simplifying compound fractions. Now that we've done all that, we're ready for the college algebra topic of rational functions. So rational functions are just y equals a rational expression. In other words, it's f of x equals p of x over q of x, where p and q are both polynomial functions. So that can be written as a sub n x to the n plus a sub n minus 1 x to the n minus 1 all the way down to a1x plus a sub 0 over b sub m x to the m plus b sub m minus 1 x to the n minus 1, so forth, all the way down to b1x and b0. Any of these coefficients can be 0 except for the first one, a sub n over b sub m. A sub n and b sub m are not 0. Okay, so there's some leading coefficient there. Of course, the whole denominator can't be the function 0. The numerator has to be can't be 0 either. If the whole numerator is 0, then you just got the constant function y equals 0. If the denominator is 0, then you got a real problem because the whole thing is not defined. Now, it turns out if we understand some characteristics of polynomial functions and a few things about that we've already seen for power functions with negative powers, we can really pretty much get to what we need to do here on rational functions fairly quickly. So let's talk about some general characteristics that they have. First of all, polynomial functions are continuous, one connected piece, but rational functions might be continuous. Of course, first of all, rational functions include all polynomials, and you could have some rational functions that are continuous that aren't polynomials. But most of the time, rational functions, the non-polynomial ones, many times those are actually have discontinuities in there. They're broken into pieces. Only so many pieces, though. There's a finite number of pieces there. And so they have some kind of, and the only places that they're discontinuous is where the breaks happen, where they're undefined, and this is exactly the places that make the denominator 0. Remember, polynomials are defined for all reals, so the numerator is always defined, the denominator is always defined. It's only in the division that you have a problem. So anytime the denominator of the fraction is 0, then the whole expression is undefined, and those will give us places where we have breaks in the graph. So if it's an x value that let's say x equals 5 makes the denominator 0, then we know if we draw a vertical line at x equals 5, then the graph will not touch that vertical line. Now there's sort of two ways it could come at that. It could come at that towards a single point on that line, which would be a hole in the graph, or it could come at that line as an asymptote, a vertical asymptote. Okay? So how do you find where these discontinuities happen? Well, you want to find when the denominator is 0, and of course that boils down to the same thing as finding the factors of the denominator. And we've talked earlier in our earlier section about finding the zeros or roots of polynomials. Well, once you find the zeros or roots of the polynomial in the denominator, you found the places where this function is undefined. How do you tell apart the vertical asymptotes and holes? Well, if the reduced version of the fraction, so you take the original version, if you plug in and you get a non-zero number on the top and a 0 on the bottom, then that's definitely a vertical asymptote. If you get a 0 on the top and bottom, then you should be able to reduce the fraction a little bit. If you reduce the fraction and it still gives you a 0 on the denominator, then that's a vertical asymptote. But if you reduce the fraction and it now gives you something non-zero over non-zero, that's the y-coordinate of the hole in the graph. We'll look at examples of each kind. Now between these breaks, the holes and the vertical asymptotes, if it has any, the rational function is continuous and smooth, a lot like a polynomial function. And like polynomial functions, it can have maxima, it can have minima, it can have inflection points, but it also has something interesting on the ends that polynomial functions don't necessarily have. It could have some horizontal asymptotes or some slanted asymptotes. Okay? And that's something that you don't get you basically don't get the horizontal asymptote on the ends of polynomials. So we can have both horizontal and vertical asymptotes on some rational functions. So just like power functions, now remember when you had a power function like this, remember that first term in the numerator really kind of dominated everything, and the basic end behavior was really determined really just by that first term. And the end behavior of the denominator is determined by that first term. So when you get really, really large x's, these other terms, you can sort of cross them out, not in determining the y, because they're all important in determining what y value is there, of course, but in terms of determining the basic shape on the end, it's really determined by this first term in the numerator and the denominator, which boils down to really just one single power function there. The coefficient an over bm, and then the power n minus m over on x. And of course we know that's going to be an integer power, and we know if that integer power is negative, all those polynomials, all those power functions with a negative power, and then just multiply by some constant in the front, are going to have the x-axis as a horizontal asymptote. Okay, so that horizontal asymptote will happen anytime you have a negative power here, which means the power is bigger in the denominator. So basic rule, if the power is bigger in the denominator, then you're going to get the horizontal asymptote of the x-axis. If the power is the same, let's see, here's what I've said about the power is bigger in the the numerator. Let's do that now next. If the power is bigger in the numerator, then it's not going to have a horizontal asymptote. It's going to look a lot like this power function, and remember those power functions with positive power are going to go up on the right side. Now if you put a positive coefficient, if you have a negative coefficient, it'll go down on the right side. So we'll see this a little bit more in some examples. It'll make a little bit more sense once I get that. If the power is the same on the top and bottom, then this turns out to be just x to the 0, which is 1, and a to the n over b to the m right there becomes your horizontal asymptote. So there's your horizontal asymptote. If the powers are the same in the top and bottom, you take the ratio of those leading coefficients, and that will be the constant that you're approaching on both ends. So that will give you a horizontal asymptote. If rational functions have a horizontal asymptote, it's the same asymptote on both ends of the graph. Remember, for example, exponential functions had an asymptote on one end, but not the other end. Okay, but if rational functions have one, then they'll be the same on both ends. Now, if the degree is larger in the numerator, so bigger in the denominator, bigger in the numerator, then it doesn't have one. If it's bigger in the denominator, then it's always approaching the y equals 0. So those are your three cases: larger in the denominator, y equals 0, x-axis asymptote. Same numerator and denominator, asymptote, ratio of the coefficients. Larger in the numerator, no horizontal asymptote. So here are our basic steps to analyzing rational functions. First of all, factor the numerator and the denominator out. We might do this using any of the techniques that we've learned before, including all of our techniques for factoring polynomials from our last section. Find what values do not reduce the fraction, however, yet. Find when the denominator is 0. The domain is all real numbers except for those x values which make the denominator 0. Now, reduce the fraction by canceling out the common factors in the numerator and those in the denominator, called the reduced version r of x. The graphs of f of x and r of x are exactly the same except for possible holes in the graph. Determine the vertical asymptotes in the holes. If the denominator is still 0 for x equals some c, okay, in the reduced version, then x equals c is a vertical asymptote. if the denominator is not 0 for x equals c in the reduced version, but x equals the denominator is 0 for x equals c in the original f of x, then c comma r of c is actually a hole in the graph. Okay, sometimes called a removable discontinuity, because you can just plug it by adding 1 point. Next, determine the end behavior by taking the ratio of the leading coefficients in the numerator and denominator. This gives you a power function that looks like g of x equals a sub n over b sub m, x to the n minus m. And that will have very similar end behavior to our rational function. If this power function has a negative power, in other words, the larger power is in the denominator, then y equals 0 is a horizontal asymptote. If the power function is constant, in other words, the powers in the numerator and denominator are the same, take the ratio of the leading coefficients for the horizontal asymptote. If this power is bigger in the numerator, then so that's, in other words, a positive power function, then it doesn't have a horizontal asymptote. But that power function does describe the end behavior. So like if it's a quadratic and has a leading coefficient positive, you know that's going to be up on both ends, and you'll see on the ends, if you zoom out enough, it'll look kind of like a quadratic. Okay, determine the x-intercepts, roots, and zeros. These are places where the numerator is 0, but the denominator is not 0. If they're both 0, then it's either if the denominator is 0, it's a hole or a vertical asymptote. Possible hole if they're both the same. They're both 0, numerator and denominator. If it's already factored, this is pretty easy to do. But if it's difficult to factor, remember you might want to do calc 0 or calc root on your calculator. Most of your calculators will say calc 0 to help you find those places, at least approximately. That can help you find some of the factors. Determine the y-intercept if it exists. Okay, and all you have to do, of course, there is just plug in x is 0 and see that. And that will be the ratio of these last coefficients, a0 over b0. Of course, if a b0 is 0, then it doesn't have a y-intercept. Then you can start to sketch the graph by sketching in the asymptotes as dotted lines and mark any intercepts, and graph the holes as open dots, and then start to make a table of points, especially near the asymptotes, and graph these. Then you can verify some of this with your graphing calculator or computer program. Be sure to choose a scale that's appropriate. You can sometimes use your table feature to help you out determine the graphing window. And your graph should show all the interesting information. It should show the asymptotes and the holes, if there are any, both vertical and horizontal. Should show the end behavior. Should show your relative extrema, the x and y intercepts, inflection points. Now sometimes it takes more than one graph to actually show all of that information, so sometimes you may need to give some multiple graphs, but try to show that. Then you can estimate coordinates of the local max and maxima and minima by doing calc maximum and calc minimum, and then determine whether the function, where it's positive, negative, 0, or the range. You can determine all that at that point. And here is sort of a template for looking at functions. You can write the original formula here, the factored reduced version here, write down what the domain, the vertical asymptotes or holes are, the power function that approximates the end behavior, horizontal asymptote, the y-intercept here, okay, the x-intercepts here, and maybe their multiplicities. And guess what? The thing that we studied about multiplicities on power functions works here too. So multiplicity 1 factor in the top, once it's reduced, if that's any x's that make that 0 will be a simple root, and the graph will go through the x-axis at that point, but it'll kind of go through straight through, kind of like a line if you zoom in close. Whereas if you see a square on a factor in the top, it's going to touch and turn around on the axis. There'll be a local maximum or minimum as well as being a root. And of course, if the power has 3 or more on the top, an odd number bigger than 3, 3, 5, 7, it'll have that, that it'll be an inflection point and horizontal asymptote there of the x-axis, as well as being a root. And then you can approximate global and local extrema, pick appropriate graphing window or windows, and do the range. You can fill out some x and y coordinates here, and you can sketch a graph. So let me work out a few examples. These examples are kind of show you some interesting things that can happen. So let's start with an easier example. F of x equals x plus 1 over x minus 2. I guess, you know what, I'll start with an even easier example that we've already studied. Probably the easiest example of a rational function that's not a polynomial function is just 1 over x. Whoops. Gotta get an equals in there. Now we've studied this guy before. He has an asymptote of the x-axis and the y-axis, both vertical and horizontal asymptotes there. That's a power function. Another way we could have written that, of course, is x to the power negative 1. If you do x to the power negative 2, that one has again the same vertical and horizontal asymptotes, but notice that another way to write that is 1 over x squared. Notice that even power in denominator is going to make these arrows point the same way on the asymptote. What's going to happen if I let's clear this out. If I take we'll go back to 1 over x. If I take this and do x say minus 5, that's just going to shift the whole thing to the right, and so we get an asymptote there at x equals 5. So those are a couple of easier examples. So let's look at this one. X plus 1 over x minus 2. Well, we can clearly see that if we plug in 2, we get 0 for the denominator, so that's not allowed. So the domain is all real numbers except for 2, which is what I've written here. And you can't reduce anything, so that means that x value will be the x equals that number will be a vertical asymptote. So there are no holes in this one. Notice none is an appropriate answer for some of these. Now the power function p of x that approximates the end behavior is just x over x, which is 1, which means y equals 1 is a horizontal asymptote. The y-intercept, pretty easy to see that. That's going to be when we put in x is 0, we get 1 over negative 2, so negative 1/2 is a y-intercept. What about x-intercepts? That's going to be when the numerator, f of x equals 0, so put 0 on the left side, but that happens exactly when the numerator is 0, x plus 1 equals 0, when this x equals negative 1. So negative 1 is the root, negative 1, 0 is the x-intercept, and it has multiplicity 1. So we should see it going through the point negative 1, 0, and it should go straight through kind of like a line. We'll look at the graph here to figure out the rest of this stuff. Okay, a little trial and error may have us going here till we figure out an appropriate window. But it looks like I tried to decide on negative 20 to 20 and negative 10 to 10. And there's the graph right there. Okay. Let me I think this is, there's some decimal points missing here. I think that's what they're supposed to be. Okay, and there's what the graph looks like. Notice we got our vertical asymptote right here of x equals 2. We have our horizontal asymptote of x equals 1. And when we're the upper right of that, we get our shape like this, concave up, decreasing up there. And we're to the lower left of that, those asymptotes, concave down and decreasing. And so there we have it. The y-intercept, 0, negative 1/2, you can see that. X-intercept of negative 1, 0, kind of goes straight through there. Multiplicity 1 root. What's the range? Well, there are no holes in it, so the only break we have is this horizontal asymptote, so it's all reals except for 1. When is y negative? That's when there's the graph below the x-axis. Well, that's going to be this piece here from negative 1 up to the vertical asymptote of 2, so between negative 1 and 2. And otherwise, where it'll be on this piece from negative infinity to negative 1, it's positive, and also from 2 to infinity. Doesn't have any extreme values, local or global, and so there we have our analyzing that graph. Let's do another one. 2x squared minus 8. Factor that. The top is 2 times x squared minus 4, which is 2 times x plus 2 times x minus 2, and the bottom is x plus 2 times x plus 3. Now don't reduce it yet. Okay? Look at the denominator. What makes the denominator 0? Well, if x is negative 2 or negative 3, that's what makes the denominator 0, and so those will be the things that are not allowed in the domain. The domain is all reals except for those. Okay? Now, reduce it by canceling out the x plus 2's. So these two functions here are going to be equal as long as we didn't cancel out a 0. Well, x plus 2 is 0 when x is negative 2. So to make these two equal, I have to really put the restriction x is not negative 2. Because look what happens when you plug in negative 2 in this one. You get negative 2 minus 2 is negative 4 times 2 is negative 8. Negative 2 plus 1 is, negative 2 plus 3 is 1. Negative 8 divided by 1 is negative 8. So you actually get a point. If you didn't have this restriction, the right side here, y equals 2 times x minus 2 over x plus 3 would actually have the point negative 2, negative 8 on it. But this one on the left would not have that. You can see that in your calculator like this. Let's takes just a second to get the calculator up. Okay, so what I'm going to do is I'm going to put in the original version, then I'm going to put the reduced factored version in. One is y1 and one is y2. Let's get rid of that. Okay, so the original version, like it was, is parentheses 2x squared minus 8. Be sure you put parentheses around the numerator and around the denominator, because remember the fraction line there is a grouping symbol. So I put that as y2. So y3, I'll put the reduced version over here. Parentheses 2, parentheses x minus 2, close, close, divided by parentheses x plus 3. Now if I look at my tables, if I've done this right, the tables should match. And let's just start at, that's good. We'll just start at negative 5, go up by 1. And if you look, the tables do match. Everywhere except one place. They both still have an error at negative 3. That's going to be a vertical asymptote. But this one here, the negative 2, negative 8, that is a point on the y3 graph, but not on the y2 graph. So that's a hole in the graph on the y2 graph. So if I take this new one here, try to plug in the things that are not in the domain, if you still get a 0 denominator, that's going to give you right here a vertical asymptote. On the other hand, if you plug it in and you get a number out, that's going to give you an ordered pair for a hole in the graph. So when you see the graph, you're not really going to see the hole in the graph. I'm not sure what window is going to be good here. Let me start with Zoom Standard. Actually, I don't need both of these anymore. So let me just get rid of this one here. Let me just turn it off. And graph. Okay, that's not a bad window. We might want to zoom out just a little bit. And let's go -20 to 20. And maybe negative, well, we want 1 there. And let's go up in 5s. And down here we'll go from -15 to 15. It's not quite a square window, but close. Okay, you can kind of see the horizontal and vertical asymptotes a little bit better on that one. But notice you don't really see the hole anywhere. You'll see it if you try to trace it and put in that value. Try to trace -2. It'll just leave a blank there. Okay, but you might not run across that if you're just trying to move around here. In the table, however, you will see the hole. And again, the table, you see the vertical asymptote on the graph. As you can see, there's a break there, and you can see it going up vertical there. You don't see the hole on the graph because, I mean, how big is it anyway? It's just one point, which is no big at all. It's just a location. But if you turn on the reduced version and simplified version here, the graphs will be the same. The tables will be the same, except for you will see the hole right there because it'll show up as a number here and not in the original. The vertical asymptotes will show up as an error both places. So now you can tell those apart. And I think that's important because I don't want you to go around after this class and people to say you don't know your asymptote from a hole in the graph. So we want to be able to sure we can at least get that much done. Okay. What about the end behavior? Well, there's a power function that would approximate the end behavior, and you just take the first term over the first term here. 2x squared over x squared, which reduces to just 2. Okay, so y equals 2 is a constant function, so that says that y equals 2 is a horizontal asymptote. Okay, where does it cross the y-axis? Plug in 0 here for x, and you get -8 over 6, which reduces to -4/3. Now you can see some of these things on the calculator again. If you just quit and did y2 of 0, we get that, which we can change into a fraction form, is -4/3. Okay, so -4/3 it is. We can see that on the graph here at -4/3 if we 0 -4/3. You can do as a trace here. Trace, there it is, 0, -1.3 repeating. The horizontal asymptote you can kind of see by tracing way out to the right. Let me do trace and then 20. Put us all the way at the end, and we're not there yet. So, but if we could zoom out and then kind of keep going to the right, you're going to see that getting closer and closer and closer to 2. Okay, and so maybe a better window would be going along. Better if we look at this at our table here, as we go way out to the right or left, these y values should be getting closer and closer to leveling off to be 2. Out here to the right, they're a little bit below that, but as we go further and further out, they get closer and closer to 2. So let's do this. Let's go out. Let's start at 10 and go out by 10s. Go out a little faster. Okay. Now it may approach it pretty slowly, but you can kind of see, I think, that this is starting to kind of level out a little bit, and it's getting closer and closer to 2 as we go on out there. Alright, let's see what else. Well, let's go to Xintercepts. That's pretty important. Let's look in the reduced version and see what makes x 0. Now notice there, okay, let's put that in, and notice x equals 2, you can pretty clearly see in that factored version is going to make y equal to 0, and so that is your x-intercept. And again, you can see that on the graph a couple of ways. when you look at the graph, that's going to be the one and only place it crosses the x-axis over here, right there. And since that was a nice number 2, I should be able to just do trace. Oops. Let's do trace and put 2 in. I should get y is 0. Yep, sure enough. And of course we can see that in the table. If we make sure that the table has 2 in it, let's just start it at 2, then you'll see it as a 0 on the y. Of course, when x is 0, you'll see the y-intercept there. Okay, so there's the graph. Here's a Graphmatica view of it with the table there, and again showing you the error message and the no error message on the reduce there, so you can tell the asymptote from a hole in the graph there. What's the range on this one? Well, notice when I graph this, I have to graph by hand. I didn't do this in Graphmatica. It's not going to show you this. I did this by adding a point here, and I don't know, hopefully got it in the right. That actually moves around, so let's make sure I've got it in the right place. It's supposed to be at -2, -8. Yeah, it looks like it's at least approximately in the right place there. So, you see your vertical asymptote here. Horizontal one, what was the vertical asymptote? X equals -3. Horizontal asymptote, y equals 2. Hole in the graph, -2, -8. So what's the range? Well, you get almost everything, but it doesn't have this y value where the hole is because it's not picked up there or anywhere else. So it doesn't have -8. And it doesn't ever cross the horizontal asymptote in this case, which was 2. So it's all reals except for 2 and -8. Let's look at another example here. Okay, x cubed minus 27 over 10x squared plus 30x plus 20. So here we factor the top as a difference of 2 cubes, x minus 3 times x squared plus 3x plus 9. Here I'm just factoring over the integers, and the bottom is 10 times x plus 2 times x plus 1. This x squared plus 3x plus 9 has 2 non-real roots, which are actually the 2 non-real cube roots of 27. The real cube root of 27 is just 3. And so what do we get? We get all real numbers except for -1 and -2 as the domain. There's no canceling, so they're both going to be vertical asymptotes. So that means there's no holes. What power function approximates the ends? Well, x cubed divided by x squared is x, then 1/10, so you get 1/10 x, or 0.1 x. Okay, they're not. So what this means is there's not going to be a horizontal asymptote, because this would have to be x to a negative power, which would give you the 0, the y equals 0, the x-axis is an asymptote, or you just get a constant here. But this does tell you that we're going to get a slanted asymptote with a slope of 1/10. Actually, if you want to find out exactly what that is, what you need to do is do your long division here and divide this out, and you'll get a linear polynomial plus a fraction, right? Remainder over divisor. And that linear polynomial is what it actually approaches on the end. In fact, in general, if you'll divide out long division, you'll get a polynomial and a remainder, and that polynomial is exactly what it looks like on the ends. Of course, that polynomial looks like pretty much just its first term. So when we find f of 0, we find the y-intercept. And of course, it's easier to see that probably up here in the original version, because all this part just with x's cancels out. You get -27 over 20, which is -1.35 for the y-intercept. We'll get this greater than and less than 0 stuff a little bit later. Let's go ahead and get the x-intercept now, though. The only place that makes the top 0 that's a real number is x equals 3, so that's a root of multiplicity 1, so it's only going to cross the x-axis one time. So let's take a look and see what the graph looks like. Here's what the graph looks like. You got 2 vertical asymptotes, -1 and -2. So that's this grid line right here and this grid line. In between those, it's got to be somewhere. So we had to go quite a ways up here. Notice this is 10. We need to go up around 12, 13 here just to even see the bottom of this thing. So I need to go up like, what have I gone up to? 35 for the top, and down to like 25 for -25 for the bottom, and then I could see this part here with the vertical asymptotes there and the local minimum there. Now actually there is no local or global minimum. This piece on the right takes in all real numbers. It goes down forever. You can see that for sure. And we know this is slanted with kind of like a line with slope 1/10. In fact, there is a slanted or oblique asymptote there. How do you find that oblique asymptote? Actually take this, divide the bottom one into the top with long division. The polynomial you get will be it'll be 1/10 x plus some constant, and that will be exactly the slanted asymptote there. Okay, a couple more examples. Here's one. Okay, and we factor the top, x minus 2 times x plus 1. The bottom is x minus 2 cubed when you factor that out. Notice that if you plug in 2, the denominator is 0. In fact, you get 0 over 0, but when you cancel out the x minus 2's, this one normally 0 over 0 could give you a whole, but it doesn't in this case, because even after we cancel out that x minus 2 in the top, there's still another x minus 2 left in the bottom. So the denominator is still 0 when you plug in x equals 2. So that is x equals 2 right here is our vertical asymptote. X squared over x cubed is 1 over x, or x to the negative 1. So this is going to look a lot like x equals 1 over x, in other words, on the end. So we know on the right side is going to come down to the asymptote, decreasing down that. And on the left side it's going to be coming from below, coming up this way. So it's actually concave down, decreasing here. It's a little hard to see it, but right in here there's a minimum and it comes back up. So it comes down, minimum, and it goes back up. Okay? And we might want to you could even maybe zoom in a little bit right in there and see a little bit better what's going on. The y-intercept is when x is 0. So from the original version we see all those are 0. You get negative 2 over negative 8, which is 1/4. So 0, 1/4, that's right here on y-axis. How about for the x-axis? Well, after you've canceled everything out, you see x equals negative 1, and it's going to make y 0. And so it only crosses the axis this one time at negative 1, 0. So on the ends it's asymptotes. There is a minimum right in here, and I can approximate that. That's a local extremum, and it's actually a global extremum too, because if you look, that's the lowest the thing gets altogether. So the range is actually from there up. Let's do another one. Alright, this gets kind of big in the top. We've got a 4th degree polynomial and a 2nd in the bottom. So factor the top out. We use some, well, this one's a little harder to factor, but you might look at it. You might just graph it first and then see the factors. This indicates it crosses the x-axis at negative 2, negative 1, and 1. And, well, you can see them going through at 1 here. And we need to zoom in on this part, which is this close-up, and see the negative 2 and the negative 1 there. See the simple root there, multiplicity 2 root there. And that's going to be what we expect to see. Multiplicity 2 root at negative 1, that's shape, right? And 1 here. Now, it's harder to see from the end behavior and the big overall shape. We lose that detail right in there. So this is a case where you need a couple of pictures to see everything that's going on. Just going to get rid of this. Okay, now, the thing that's kind of interesting I want to show you about this one is, look at the power function that defines the end behavior. X to the 4th over 3x squared is 1/3 x squared. So look at this. Do you see that x squared shape on the ends? See how on the ends it looks a lot like a 1/3 x squared? It'll exactly approach a polynomial, kind of like an asymptote. We usually use that word for reserved just for lines. But it has a limiting curve that's exactly a polynomial, that's a quadratic. To find that one, that limiting curve, we would divide out the long division here, which I don't want to mess with right now. But if you do that, you're going to see But you see the basic quadratic shape? Now in between doesn't look at all like a quadratic. We got a couple of vertical asymptotes here, and notice they happen when the denominator is 0. It factors as 3x minus 2 and x minus 2. So that's, no, this one is 2/3, and this one's 2, or what makes those 0. So x equals 2/3 is your asymptote right here on the, right here, 2/3, and the other one is at 2 right here. In between the two, it kind of comes down like that, decreasing. So that piece by itself is all reals. No minimum on that one, some kind of inflection point somewhere in there. And this one on the right side has a local minimum right in here somewhere. And this one here, it's harder to see, but if you zoom in, it has a minimum and a maximum locally. But this piece eventually gets all reals. This piece gets all reals. This piece only goes from that minimum up. But overall, all reals are used. So I wanted to show you this one because you can see that nice little looking quadratic, parabola kind of shape on the outside part. Also, this is a good one to show that sometimes it takes more than one picture to see things, and it's another one to show you. Another thing that this shows you is that the roots of the numerator, after it's reduced, have this are x-intercepts, and the shapes, the multiplicities have something to do with the shape, just like they do in polynomials. So when I see -2 and 1 are simple roots, you see that on the graph because this kind of goes through like a line, and so does this. But this one at -1 is multiplicity 2. It's touching and turning around there. Alright, one or two more here. So 5x over x squared plus 1, one I wanted to notice on this one is that this one does not have any zeros for the denominator, at least any real zeros. To make the denominator 0, you'd have to make it I or minus I. So the domain on this one's all reals. So I wanted to do this one to show you that the domain could be all reals even if it's not a polynomial. So this means it's not going to have any breaks in it at all. It's going to be continuous, and so that means no vertical asymptotes or holes. What does it look like on the end? Well, it's going to look like 5x over x, which is 5 times x to the -1. And so look at the ends, it looks a lot like x to the -1. Actually, this one is an odd function. You can check that out. Put in minus x in place of x. The bottom stays the same, but the top changes signs, so the whole thing changes signs, which means it's going to have origin symmetry. Whatever it looks like in the first quadrant here, you're going to get a reflected image down here in the third quadrant. Okay, this one has these symmetric maxima and minima. One's at -1, -2.5, that's the minimum. In fact, that's a global minimum. That's the lowest altogether. And at 1, 2.5 is the global maximum. So the range on this one is actually just from -2.5 to 2.5, but the domain is everything. So you can have it be all connected. Also, this one points out that the graph can cross the horizontal asymptote as well. So here the horizontal asymptote is the x-axis, but it actually crosses it here. It's not going to cross it way out on the ends. That's what an asymptote is. It's going to approach without crossing. But it's really only asymptote when you're talking about at the very ends, way out here. In the middle part, it could cross that asymptote. Okay, so there's several examples. Notice I'm heavily using the graphing calculator as well as some algebra to help me analyze these things. So here are a number of problems here for you to practice, a bunch of examples, and let you practice these. There's one real world problem I'll let you read, and then there's a set of practice problems, and if you go work through these, down at the bottom down here are solutions to those practice problems. So I encourage you to at least work those practice problems and check them. Really should work all the problems in this video. So hopefully that'll give us a nice little introduction to rational relations, and you can use that to help you study. Of course, don't forget to read your textbook and look at the materials that you have there as well.